Hello. Part B, we got the lights back on. It's the same example, so without further ado. The theoretical mean, or excuse me, the theoretical model for the sample mean will be approximately normal if one of two conditions are met. If you have both, so much the better. Okay. Now we saw in that dot plot, sure look normal, right? We're trying to convince you with a simulation that it's normal rather than just you taking our words from it. Requirement number one, the population you're sampling from is normal. So what we're trying to zoom in on is what's the distribution of y bar. And one way to get there is whatever variable we're working with, that variable is normal. IQ scores are normal. Because IQ scores are normal, the sample mean will be normal. And it probably says that right below, so let's flip the slide. I like the way that I think here. IQ scores follow a normal model. Therefore, no matter what sample size we would choose, say I took 4 students, say I took 40 students, 400, doesn't matter. Because IQ scores are normal, no matter what sample size I choose, the sample mean will also follow a normal model. At Cecil, we just happened to take 100 students and then simulate. You know, we had to imagine taking all these repeated samples. We'd never do this in reality. Okay? Sample mean will also be normal. And let me summarize this right here. If y is normal, so is y bar. That's like the easy way to get there. Right? If y is normal, so will be y bar. How about the other way? Not every variable is normal. What we have to realize is just because we're working with quantitative data, that doesn't mean that the variable will follow a normal model. Requirement 2, if you take a sample size of at least, we'll say 30. Some textbooks give 25 or 20, some give 40. We'll just call it 30. If you take a sample size of at least 30, here, comma, y bar will be, throw approximately in there, approximately normal. Close enough where it won't matter. We'll show you this in class. We've got some cool simulations we can show you to convince you of this. Don't confuse this with the 10 successes and the 10 failures. When we're working with quantitative variables, you need a sample size of at least 30 or the variable looks normal. If you went back to categorical, now you have that success failure, so the 10 and 10. Students always confuse these two. Remember, what kind of variable are we working with? Now, in the back of our minds, checking each of those conditions does roughly the same thing. But what kind of variable, right? Either 10 and 10 or sample size of at least 30. Little example just to think about this. And we'll build on this during class time. Example bottom of the page there. At Cecil College, we'd like to run a hypothesis test to see if the mean age of students has increased since it was last officially announced at 27.5 years old. Okay, so suppose 3 years ago they took a census from registration records and announced that at Cecil the average age is 27.5. Here's what I'm thinking. What's the variable? The variable is age, right? If I ask students, tell me your age in years, it's the variable. And what kind of variable? It's quantitative. I know this seems awfully basic, but at the end of the course, students sort of forget the easy stuff from the beginning of the course. Not you students, former students would forget this, right? Variable's age, and it's quantitative. Think about part B. What's the likely shape of the distribution of student ages? So you look around the hallways, and what do you see? You see a lot of 18-year-olds, a lot of 19-year-olds, a lot of 20-year-olds, right? And maybe a few less 21-year-olds, maybe go up to 30-year-old, maybe even fewer 30-year-olds, maybe go up to 38 years old, maybe fewer of those. And so the likely shape is what? We've got a ton of data at the small values, and as students get older, there are fewer older students at each older age in general. So that shape is probably going to look like that, right? Skewed right for sure. Long tail to the right, lots of data piling up at our 17, 18, 19, 20, 21-year-olds, of course, and then as you get older. Now, do we have 60-year-old students? Of course. Are there lots of 60-year-old students? Not that many, right? So it'll taper off, skew to the right. Part C, if we'd like to perform our hypothesis test. Remember, we want to run a test to see if the average age is increased. How many students will we have to sample? My goodness, you tell me 10 successes and 10 failures, you're going to be in big trouble. At least 30. Quantitative. At least n equals 30. If you can afford more data, if you have more time to collect data, go for more than 30. At a bare minimum, for the normal model to kick into gear, we'll need 30. Okay? Easy enough. Flip the page. What are those conditions? They're almost all the same, just the one is different. Well, two are different. Always thinking about the variable. What are the rules to model the sample mean y bar with a normal model? The variable is quantitative, and we are investigating the what's sample mean there? It's a long line. I wonder what I was thinking in my notes. I guess I was thinking that. It's good for me. Right? I was going to just put mean, but the line was too long. Variable is quantitative. We're looking at sample means. The sample is what or what? Sample is normal looking, right? The data is normal looking, or at least size 30. Sample sample is random. All right, I was getting ahead of myself. What kind of data should we be collecting? I was so worried about 30, right? The sample we've collected is random, or at least unbiased. So we need to collect good data. Think about the age problem. If I only took night students, which are the classes I typically teach, would that be an unbiased sample? It wouldn't, because I think typically older students might take the night classes. So that would be a bad sample, would be biased towards older ages. Samples should be less than 10% of the population. And finally, here's the one I was thinking of back in B. We're confident that the population is normal, or we have taken a sample size of at least n equals 30. All right, glad we clarified all that. I do want to make one point about this normal here. How do I check that? Say you collect some data, right? Once I have that data, and if I'm not sure that the variable is normal, what should I do with that data? I should graph that data, right? So don't go assuming, as some of my students are currently doing in this present semester as we're taping this, they're just assuming that the data is normal looking without graphing it. So to be confident that the population is normal and you've collected your data, graph it. You should look at a histogram for that familiar bell-shaped curve. And you should also be checking that QQ plot, quantile plot, the one with the dots. The closer the dots are to the diagonal line, the more likely it is that the normal model is the correct model. All right, so just don't make a blind assumption that, sample size was 11, I'll just presume it was normal. Not good practice. All right, number 2. If the conditions are met, a normal model is appropriate for modeling the sample mean. We need the mean and the standard deviation. how can we say all this? So, y bar will be approximately normal. This just says y bar follows a normal model, approximately normal model. Here's the symbols. I need a mean, mu. The mean of y bar. Mu sub y bar. I know it's sort of strange. I'm taking what's the theoretical mean of the sample mean, but it's correct notation. This equals the mean of y. So we've got a y bar here and just mu of y just here. What this says, think of the IQ example. If the true IQ at Cecil College is 100, when I take samples, I should average 100 in the long run, right? Sometimes my sample might be above 100, sometimes it might be below, but on average, it should target 100, which is the true mean. I need a standard deviation, sigma of y bar. I don't know why, students always forget to do this. If we're cooking up that y bar model, I need the standard deviation of y bar. I take the original standard deviation and I divide it by the square root of n. Okay? It's not hard to do, just don't forget to do it. Right? So if the conditions are met, this will be the appropriate normal model for y bar. Now at the bottom, we would be remiss if we didn't mention this. My opinion only, sort of like a trivia fact, but it's the central limit theorem, and at the intro stat level, here it is. For our purposes, bullet point, for most any population, shape, right? Shape. So think of a variable and you graph it, it looks skewed left or skewed right. Or maybe it looks uniform. Or maybe it's bimodal or trimodal or pretty normal looking anyways. The sample mean will follow a normal model as long as you take a random sample of at least size n equals 30. This is the central limit theorem for the intro stat course. Now, the reasons why, a little bit beyond the scope of this, in class we can show you simulations. It's sort of hard to appreciate this, and the simulations I don't think would translate to a video. So in class, we'll develop this idea, and it's pretty neat to me to watch it in action. Okay, so that's central limit theorem, and that's why we require that sample size of at least 30. So, all that being said, Kip Shepard will be up next to do a few examples. Thanks for watching, and we'll see you in class.